Hello, friends. Welcome back to my class 1 lecture on the Introduction to Aeronautics, Introduction to Aircraft Structures. So, we have been looking at the primary structures of an aircraft, as starting from the identifying the components of an aircraft, and also I have been taking you through various different construction aspects of the fuselage, wings, and few other stuffs like engines and landing gears. So now we'll be moving into the materials used for the aircraft construction, or materials that have been used in the manufacturing of this aircraft and its components. So this is a very important topic. So let's begin. Materials. First of all, there is a big challenge in the aircraft industry happening every single time whenever they want to select the material that is used for the construction of the aircraft components and its parts. The design department and the analysis department, usually they do their calculations on the assumption of few existing material properties, and finally when they want to meet the certain criteria, when the existing materials uh, doesn't meet with the existing materials, if they are not able to meet, then they have to procure a new material, and they have to qualify it, they have to certify it, and then they have to use it for manufacturing. So it's a lot many activities involved around this materials and manufacturing uh, manufacturing area. So this materials, coming to the materials used in the airframe construction, there are mainly steels and its alloys, aluminum and its alloys, titanium and its alloys, magnesium and its alloys, and composite material. Not the least, but composite materials are the far more advanced type of materials, and very complex in the analysis. Steel and its alloys, they are mainly used for the attachment brackets, attachment lugs, and those kind of stuff. To give you a very quick example, for example, an horizontal stabilizer that is attached to the vertical stabilizer, there is a big set of brackets, steel brackets, it is to which it is attached, and aluminum alloy. Aluminum alloy are mostly the external structures, skin panels, longerons, spars, these all ribs, they are all aluminum alloys. And as you know, that steel is three times stronger than aluminum alloy. Even steel is also used on the wing box, where the wing um, is wing at its root attached to the fuselage, wing and fuselage junction. And titanium alloys are used in the engine components and in the landing gear components, when where there is a temperature related creep stresses, or temperature related very high temperature related stresses, or high temperature type of loading involved. And magnesium also same, on the engine parts. And then composite material is a very good alternative to aluminum alloy. Still, there are a lot of coupon testings and lot of things going on in an aircraft, in typical aircraft industry, where they want to certify the composites. They Each aircraft industry has to do the composite testing, coupon testing, in order to get the Federal Aviation certification to for them to use on their aircraft. So without the testing uh, results, the authority is not going to accept the composite material to be used on an aircraft. So composite materials, they they have a very high strength to weight ratio, as I mentioned earlier, and very expensive in uh, manufacturing, or expensive in processing them. So right from the, whether they are created from the vacuum bagging, or it's resin transfer injection or resin transfer molding, whatever may be the manufacturing process involved to manufacture them, right from the procurement of the raw materials. It is a very costly, sorry, it is a very costly affair for the aircraft industry to handle these composites. And also some of the composites are very toxic, and they have to prepare a special type of environment, a dark room kind of thing, where only access to the limited number of people and stuff with the proper personal protection equipments to handle the composite materials. So aluminum alloy, aluminum has been used in the industry. It's for a very very long time. As you know, like it is the one of the cheap rival of the composite material. And due to the advent of the technologies, and to the advent of the manufacturing methods, people want to increase the payload of the aircraft, so they go for the aluminum alternative, which is composite. So some of the material properties, what we can expect or what we need to be considered while designing an aircraft, are the strength to weight ratio, and the lightweight is also the strength to weight ratio, which is related to the strength to weight ratio, and also the corrosion resistant. So they should consider the material to be corrosion resistant, or they provide a special type of coatings in order to make it corrosion resistant if they can't find any alternative. And also it should be non-flammable material, and high quality is less with the voids and defects. So they have a quality department within each aircraft industry, where they meticulously check the quality of the material that is being used on the aircraft. Any outdated materials will be made obsolete, and the for any changes involved, they for any changes made, it involves the paperwork being released and being certified by the approval organization or the related airframe authority, in order for them to proceed with the new material to be used on the aircraft. So coming to the stress point of view, or the structures point of view, you can see that I have put the stress strain curve showing the composite material and the metallic materials. Composite are very strong materials, but it undergoes a brittle fracture when it exceeds the yield strength. But metallic materials, they have the elastic portion, and then they undergo a strain hardening or work hardening of the plastic region. So little bit of yielding, sometimes little bit of yielding is allowed on some of the structures, and then ultimately they fail when they pass the ultimate stress. When the loading on the component pass the ultimate stress, they go to necking and fracture. So just having talked about the brief on the type of materials we used. So this is on a typical commercial aircraft. So the modern day transport, what we use on the modern day transport are mostly aluminium, and with the steel and the titanium, that is for the spars, stiffeners and skins and those kind of stuff. And also there are composites coming into picture, used for non-carrying parts, spoilers and fuel tanks. This was the picture somewhere around say about 15-20 years back. So still it is still valid for some of the modern day commercial transports, but the mostly the fighter jets and the latest transports use carbon composite materials, in addition to the glass fiber, GFRP, which is glass fiber reinforced plastics. They also use carbon composite materials, which is very lightweight and also very strong, at times very stronger than the aluminum metallic materials itself. So this is a Boeing 787. You can see that 50 percentage of the aircraft is made using composites. As I mentioned earlier, like carbon composite CFRP plies, carbon fiber reinforced plastic, which is a carbon composite. Carbon composite provides a very tougher strength equivalent to the isotropic properties. They arrange in a such a fashion that quasi isotropic lamina they call it, provides a very equivalent strength to the metallic materials, or at times greater than that. So you can see the distribution of the materials in terms of percentages used on this aircraft, just to have a feel, just to have a visualization how much materials have been used on this aircraft for the uh, for manufacturing. Now, moving on to the having seen the materials, now we would moving on to the loads and the stresses, what kind of stresses it would develop. This is just a brief, but we are going to discuss in depth and in detail during the part of the course and during the course. So first of all, coming to the loads, as you might have realized that fuselage is cabin pressure loads, because fuselage uh, is pressurized. So in order to for the passengers, in order for the conditions that is susceptible for the passengers, cabin crew, and the baggage, these are pressurized, and the pressure loads within the fuselage act on the frames and stringers and the skins of the fuselage. And there are also combined loads from the wing box. As I mentioned, that there is a junction yeah, from where like wings are attached to the fuselage, and also there is a load coming on from the stabilizers and rudder. Wings wings take the aerodynamic pressure loads. They take bending, torsion, and shear, and the stabilizers take the aerodynamic pressure loads, which is bending, torsion, and shear again. So what's happening is all those the loads to which an aircraft is subjected, they have the redistribution within the different types of structure, and try to resist those loading in a well-defined strength and stiffness criterias. So we now we'll see the loads on the specific components. Spars mainly resist bending and shear, and stringers, longerons, and shear. Sorry, stringers or the stringerons and longerons, they take bending. Ribs take shear, and whereas fuselage and wing skin, and mainly the skin panels, take the in-plane axial stresses, which is tension and compression, and the circumferential hoop stresses is mainly due to the cabin pressure loads and the fatigue loading. Obviously, fatigue loading is due to the tension loads, and the loads due which cause buckling, which is the compression loads. So basically, skins take, whether it is a fuselage skin or whether it's a wing skin, they take the in-plane compression and in-plane tension, along with the in-plane shear stresses, shear loads. Whereas the beam spars are the beam typical beam type structures, which take both bending and shear, and stringers are very small beams with like an axial, just you can say the flanges of the beams, they take primarily bending. And ribs are mainly like considered to be the webs of a beam, to be idealized as a webs of a beam, so they take primarily shear. And when designing the airframe structure, the engineer must consider some of the things in mind. So the most important uh, the criterias or the most important thing that needs to be considered are strength, stiffness, and stability. These are three S: strength, stiffness, and stability to be considered. Strength, it's governed by the strength theories. For metallic materials, we use maximum principal stress theory or the von Mises Henke von Mises theory, and for the composite material, we use Soy-Hill uh, theory or modified Soy-Hill and Soy-Wu, and then sometimes some of the industries might use maximum strain theory. They test their coupon. They do the coupon testing, or they do test their coupon composite coupons based on the strain rate. So they might be using the maximum strain theory and Hoffman theory. Some, yes, there are industries that use the Hoffman theory as well. Hoffman Helsing criteria and those kind of stuff. Uh, and moving to the stiffness criteria, stiffness criteria drives the displacements and deflections of the aircraft structure, whether it is an external or whether it is an internal structure. So, for example, if it is an internal structure, there is a galley or a galley monument which is goes inside the uh, cabin, like the deflection needs to be within 1 inch. They needs to be within 25 millimeters, which is 1 inch. So in order to avoid in order to avoid the interference with some other cabin parts or cabin components. And also wings have their own deflection criterias. It might be say, for an example, the aircraft manufacturer may say that design the wings so that the deflection doesn't exceed 10 inches. So something like that, they don't have, they want to meet the federal aviation requirements in order to for them the aircraft to achieve the certification. But they do allow some sort of flexibilities in design, but the criteria needs to be met. And again, the stability criteria, the uh, stability criteria is basically to avoid all buckling scenarios on the skin stiffener regions. Like it depends on the distance between the two stiffeners supporting the skin panel. So we need to avoid all types of buckling, whether it is a bending buckling, shear buckling, or axial buckling. And also safe fail and fail safe structures come into picture when designing an airframe. Safe fail is the multiple load path structures, but suppose if one fails and there will be the another component has a backup that would take up the loading. And fail safe is that whenever there is, it's not a multiple structure, it's not a multiple load path structure. Suppose it fails, and then what happens is the rest of the structure must support, or else it totally fails. So that's the end of the class 1 lecture. So thanks for listening.